Okay. Good evening, everyone. Welcome to the problem solving session. The first solving session for the computational complexity course on NPTEL. And okay. And my name is Bhabedeep Rai. Okay. I'm a PhD scholar at IIT Madras. And we'll be having these problem solving sessions on Tuesdays, every Tuesdays, and at 6 p.m. to 8 p.m. All right. Today is the first problem solving session, so it may be shorter, but yeah, these problem sessions are aimed to help you solve the assignments and maybe get a deeper understanding of the lectures that are already there. And these problem solving sessions will also be uploaded. These will be recorded and uploaded. In case you miss any problem solving session, then you may obviously watch those videos. But of course, the advantage is that if you watch, if you attend it, then you have a live interaction, and then we may discuss together. Okay, so let us begin. So the week one content was on the complexity classes, and P, NP, right, and reductions, and a bit of completeness. So I'll be focusing more on solving problems rather than the theory. Earlier I used to do a bit of theory as well, but from feedbacks from the students, they were more interested in solving the sessions. But of course, if you want and if you let me know, then I'm happy to discuss more theory as well. And of course, so let's just directly begin. So just a quick recap. Okay, what is complexity theory? Complexity theory is the study of it's the mathematical study of problems and categorizing problems according to their hardness. Okay, so you have different problems. Okay, by problems I mean computational problems, and you can actually study that problem and tell that, okay, this problem is hard, and you can take another problem and say that this problem is actually possibly easier. Okay, so hence what you have are complexity classes. What are complexity classes? These are categories of problems, okay, computational problems, according to their difficulty or hardness. Okay, loosely. And two such examples are, of course, P and NP, right? And let's just quickly define them. P are those problems, set of problems. And what are problems? Problems are equivalent to languages, okay? And what are languages? These are sets of strings, okay, over some alphabet. And these are problems that can be solved in polynomial time, okay, on Turing machines, or equivalently by algorithms, okay. And NP, okay, these are again set of problems, okay, that can be solved in non-deterministic polynomial time. Okay, and what is non-deterministic polynomial time? Well, you have one way to look at it is you have a special kind of machine called a non-deterministic Turing machine, which can make several guesses, and if a good solution exists, if the answer is yes, even in one of the guesses, yes in any one guess, then the machine outputs yes. Okay, so this can be thought of as an extremely lucky guesser. Okay, and another definition is that there is a polynomial time verifier. This is deterministic. Okay, What is deterministic? It means that there is no guessing. Once you given a particular step, you can always tell what the next step of the Turing machine is, what next step of the algorithm is. Polynomial time verifier Turing machine, okay, and such that given a certificate, okay, we can verify membership. Okay, and you may have seen examples of this. For example, the SAT problem. Okay, SAT problem. What is the problem? SAT is given a phi, whether phi is satisfiable, which means given a circuit or a formula, right? Given a formula phi, can you give it some kind of assignment so that the formula will always give a true answer? And what is an example for a certificate here? And the example for a certificate is a satisfying assignment. This may seem trivial right now, but of course, it may not be that trivial later on. We might see some examples in the course. And just for example, let's say a game of Sudoku. So Sudoku, let's say, what is Sudoku? It's the set of all Sudoku problems with valid solution, which can be solved, in other words. And what is the certificate for this? Well, the certificate is a solved Sudoku. And you can easily look at each of the columns, each of the rows, and then verify whether this works. Similarly, you can just evaluate the circuit and check whether it works. So these are all NP problems. We'll see the examples. And we'll come to reductions, okay? But first I want to solve a few questions, okay? So here's the question. The question says, show that the following languages are in P. Okay, this is a simple question. The first language is called connected, which is the set of all connected graphs. Okay, what is a connected graph? A graph is connected if every pair of vertices u, v, and g are connected by a path. Okay, so for example, we all know what a graph is. It consists of vertices, and there are edges between the vertices. Okay, in case someone does not know what a graph is, and this is what a graph looks like. Okay, in a diagrammatic representation, and let's say this is my graph G. I say that this graph is connected because from every vertex I can reach every other vertex. Okay, I can, let's say, take this path and then take this path and then take this path to go from here to here. Okay, this is a connected graph. What is an example of a non-connected graph or a disconnected graph? And this is an example, because you cannot go from U to V. No path from U to V. Okay, so this is an example of a disconnected graph. And just for information's sake, these are called connected components. So if your graph has just one connected component, then your graph is said to be connected. So you want to show that this is in P. In other words, you can have a polynomial time algorithm on the input, okay, on the input size, to say whether the graph is connected or not. Okay, and so any idea how we can check whether this graph is connected or not? Any simple algorithm?
Yeah, breadth first search or depth first search?
Yeah,
traversal.
Right, good. You can just do a traversal, right? So the idea is as follows. So all of us, I hope, know breadth first search and depth of search. In case you don't know, it's okay. I don't want to go too much in depth, okay? But if you pick any vertex, the breadth first search will look like this, okay? You'll go level by level. So the level is the distance, the shortest distance between fix a node. The level with respect to that node is the shortest distance with respect to that node. Okay. For example, this is at this is the node that I fix. Okay, and this is at level 1, and this is also at level 1, and this is at level 2 because the shortest distance is 2, and this would be a level 3 because so BFS goes level by level. and DFS looks for the deepest kind of deepest node first. Okay, so BFS looks like this. BFS looks like first here, then go back, then go forward, then go back. Okay, and then go down, and then search breadth wise, and then do this. DFS is more like you keep going down and then come back, then keep going down and explore a path, then come back, and so on. You don't. You can try it offline. Look up for DFS BFS algorithms. But right. So as Vinod stated, the solution, okay, is to simply do a BFS or DFS. The algorithm as follows is fix any vertex, okay, V, in the vertex set of G. Okay, the given input is, so let's say the input is G. Okay, graph G on G V comma E. Let's say V is the vertex set, E is the edge set. Fix any vertex, and what do? I perform, let's say BFS. Okay, BFS on V. Now I don't perform a simple BFS. I modify the BFS algorithm so that I can check for connected components also. Okay, and how do I do that? I actually keep a set, okay, S of all visited nodes. Okay, so let's say I run a BFS algorithm on this particular graph. Then what do I have? I have 1, 2, 3, 4, 5. Then I'll put 1. I visited 1 first, then I'll put 1 in the visited set. Then I'll put 2. Then I visit 3. Then I'll put 3 in the set, and so on. 4, then 5, and so on. And I'll put it on the set like this. And once it ends, once the algorithm ends, I just check if the size of set is equal to size of the vertices. Because if it is in the connected component set, okay, if it is a single connected component, then all the nodes should be reachable. So if this number of nodes that are reachable are smaller than the vertex set, it means some node is there in the graph which is not reachable. So if no, okay, then I'll put no. If it is same, okay, means all the nodes are visited, which means the graph is connected, then I'll put yes. Is this clear? Okay. The next question is like, why does it take polynomial time? Well, the time complexity of BFS is something like order the number of vertices plus the number of edges, and which is obviously smaller than the size of the description of the graph itself. So it takes some linear time, okay, or polynomial time. So hence this connected is in P. Okay. So if that is clear, let's quickly move on to the other questions. So here's another question I have. Okay. Triangle free. Triangle free is the set of all graphs that do not contain a triangle. What is a triangle? It is a complete graph on 3 nodes. For example, this graph contains 2 triangles, whereas this graph does not contain a triangle. This contains 2 triangles. I want all these. I want to check whether a graph belongs to this language or not. In other words, I want to check whether this graph has a triangle or not. Okay. So anyone has an idea like how we can solve triangle free? How do we check whether a graph contains a triangle or not?
To make a count of the vertices when we get a loop. If we get a loop and check that if they are ending with 3 vertices, then probably it could be a triangle, I suppose.
Okay.
I count the edges. I count the vertices till I get a loop. Means when I get a repeated same vertex once again, and
Right.
if the count is 3, then I can guess it that there is a plausible triangle.
Okay. 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 Um. Okay. Good. So Vinod, let's say this is what you mean. Okay. I have a graph. Okay. I have a graph. Okay. I do suppose like a DFS. Okay. I do a DFS. Okay. And I traverse. I traverse the graph, and I keep a note of the vertices that I visited. And then if I suppose reach a vertex that I've already visited, and then I check, I got this vertex. Okay, but the thing is I need to check the length, and as you said, the length should be 3. If that length is 3, then I'll be fine, right?
Yeah.
Yeah. Now the question is, the analysis is a bit of a problem here, because the question is, my I may not be very lucky in traversing the graph and getting a triangle immediately, right? I may get a triangle after a lot of tries,
Yes.
right? I Because there may always be a bigger cycle, and check whether this. So the question is, given a graph, I may go across very different kind of paths, and I may choose this path, and then I may choose this path, and then I may choose this path, and so on. But let's say I would have chosen this path, then I already get a triangle, and I keep exploring this side, and then I'll end up with this triangle after a very long time. And now the question is, will I end up exploring this particular triangle within polynomial time? That is the question.
In a
Okay.
polynomial time, probably it may take more time, I suppose.
It may take more time, right? In
Yes, yes,
fact,
it may.
it takes something like n factorial time, order n factorial time,
Yeah,
right?
probably. So it's
Because
almost like exponential time only.
exactly, it's worse than exponential actually. It's around n to the
Yes,
n
yes.
time,
Worse
right?
than, yeah, n power n. It's not even 2 power n. It's n
Right,
power n. Yeah.
right. That's right. Good. Now, because I have like n choices. If this side was a complete subgraph, let's say, then I have like n choices, and then I have another n minus one choices, and so on. So it may be as bad as exponential. So, but it is a good attempt nonetheless. And anyone has any suggestions, like how to go about this? Check whether there's a triangle in the graph or not. Think of the simplest algorithm possible. BFS with some modification. Okay. Suraj. Okay. Okay. So what kind of modifications could we do? Um, we yeah, I think that could also be a possible problem. I think the way you are thinking is that you go BFS, and from, let's say, you traversed this node to this node, and then you sort of make a prediction kind of node, and then go back and remember this and do a BFS, something like that. I think that is what the lines in which you are thinking, Suraj. So yeah, that could possibly work. I think so. But okay, now here's a very simple algorithm to do it. Okay, and this is actually a brute force algorithm. Okay, so here's the algorithm. Okay, okay, algorithm input. I have a graph. Okay, with vertex set and edge set, and now what I do is, for all, okay, for all S subset of V such that size of S is equal to 3, okay, to check if S forms a triangle. How? I just look at the adjacency matrix. If yes, output yes, else no. Oh, triangle free, no, should be flipped. Output no, else output yes. Okay. Now, what am I doing? I'm just taking sets of vertices which are of size 3. Sets of vertices which are of size 3.
Got got it. Got
Got
it.
it, right? Okay. And so I'm just taking 3 vertex at a time, then another 3 vertex. They may overlap also. I may take, next time I may take this, okay, and so on. And how many such choices are there? There are n vertices, let's say, and you're choosing 3.
NC3.
Yes, NC3, which will be, something like n minus 1 and minus 2 divided by, some factorial 3 to 1, something like that. And this is order n cube, which is polynomial.
Polynomial.
Right, good. So you can see that this is actually a brute force approach. You're going across all three size um, complete graphs. Okay. Now, okay, I've not, okay, now it's clear to everyone, right? This takes polynomial time. Triangle free is in P. Right. This is clear, right? Okay. Rahul, Suraj, Pradeep. Okay. And yeah, Vinod. Right? Okay.
Yeah, it's clear. Clear.
Okay.
You can go for it.
Yeah. Now, so triangle free is in P, but I didn't put it as a question, but I just want you to make a note, okay, that if instead of triangle free, okay, triangle is a complete graph on 3 vertices. Let's say I ask you about a complete graph on arbitrary vertices. Okay, so I'll write it as complete free or just complete. Okay, complete, which means complete. Okay, let's write complete free is the set of all the graphs where G does not have a complete subgraph of size k. So G comma k. It does not have a complete subgraph of size k. And if I take its complement, complete free complement, what does it have? It has all those gk such that G has a complete subgraph of size k. If I do the complement, G has a complete subgraph of size k. Now, I hope you can connect this. Have you seen this before? Have you seen this problem before? It has a complete graph of size k.
No, when
I
heard
think
of
it
this.
is NPC.
Right. Okay. So just to recall, good. This is NP complete. That's right, because this is nothing but the click problem,
Yes, yes.
right? And yeah, this is NP complete problem. Okay. And it was briefly mentioned in the week 1, but I think you'll extensively see it in this week 2. Okay. So this is a click problem, and you can already see that when I talk about a general k-sized graph, okay, general k-sized subgraph, then it becomes NP complete. It becomes much more harder. But if I was talking about triangle free, or let's say this C4 free, okay, or let's say C5 free, these are all complete graphs, but they are of constant size, and them I can do in polynomial time. But as soon as this k becomes arbitrarily, the user gives it as an input, say, then it becomes so much more harder. I cannot use this brute force algorithm, because if I say, if k is given as, let's say k is given to me as n by 2, then it will be something like n choose n by 2, which is already some order n to the n by 2, which is really bad. I cannot use that particular algorithm. Okay, and there is a good amount of research on finding algorithms, approximation algorithms, say distributed algorithms to solve the click problem. Okay. Anyway, that was just an offhand comment I wanted you guys to note. Okay, on the difficulty of this click problem. Now, okay. So here is another problem: bipartite graph. I hope everyone knows what a bipartite graph is. A bipartite graph is a graph which looks as follows. You have a graph. Okay. Okay. Someone wants to join. Okay, good. Okay, you have a particular graph, okay, which looks like this, and you know, if I can partition the vertices into two parts, let's say the red part and the blue part, so that there are no edges between a red vertex and a red vertex, and there is no edges between a blue vertex and a blue vertex. Okay. So this is the bipartite. Okay. Now what I want to do is bipartite, which is the set of all bipartite graphs. I want to check whether a graph is bipartite or not. Okay. And okay, this one I'll just quickly tell you. I'm more interested in the next problem. So
I think it is a kind of independent set finding.
It is a kind of independent set. Good. Okay. So Rahul, why is it related to independent set?
I think we are partitioning the set into two subsets, which are independent. There is no connection between these two sets.
Okay, but
No
that is
vertices, sorry.
okay, good. But that is a huge claim to make, Rahul, because independent set, as you know, is NP complete.
NPC.
Right.
Yes.
And here we are claiming that bipartite is actually polynomial. So you'll end up proving P equals NP. But I like that you see a kind of a connection between them. But just to jog your memory, independent set is a set of vertices. Good. But I can see where you get the connection. So it is a set of vertices which do not have a edge between them. So this is an independent set. That is correct. As in if you take any of the two partitions, okay, either of the two partitions. For example, if I take this is an independent set. Oh, sorry. What am I saying? If you take any candidate from here and another candidate from, oh yeah, that's right. If you take this is an independent set, or you take this is an independent set.
Yes.
Right. But the other way around is not true. Any independent set need not be a part of a bipartite graph.
Yes.
Right. Good. But yeah, these
This is only in one direction.
It's only in one direction. Exactly.
Yes.
Right. So it becomes.
It is necessary, but not it is sufficient. I think.
Exactly. So we can already see kind of why independent set may be harder than bipartite, because this is like a smaller instance of the independent set problem. Yes. But good. Okay.
Because it is just a constraint with the that we are going to find the bipartite.
Right.
Only two sets.
Right. Good. Yeah. Okay. Good. So an algorithm for this. Okay. Can any of you suggest a simple algorithm to check whether a graph is bipartite or not? Let's say I give you a graph. I want you to check whether it's bipartite or not.
I think if the graph is two colorable, then it is a bipartite.
Right, but then how do you solve two colorability?
Because I can use marking.
Yes, you go marking. Okay. Right. Okay. So I'll do this algorithm without mentioning two coloring at all. Okay. But underlying principle is the same. So what you just do is the algorithm is as follows. Okay. So pick any vertex. Pick an arbitrary vertex. Let's say V. Okay. And what you do is put V, that particular vertex, in set S. Okay. Now what you do is put all the neighbors of V, okay, whichever it is connected to, in a set T. Okay, now repeat this certain sequence of operations for vertices in T. Okay, and if you come across a vertex, if we encounter a vertex U which is both in S and T, then we have that it is not bipartite, else it is bipartite. So the principle is the same, right? Rahul, I hope you can see that this is you were talking about the same algorithm, right?
Yes, yes.
Yeah. So okay, so if you have a particular graph, you want to check whether it is bipartite or not. Okay, what I'll do is I'll pick a vertex and put it in set S. The neighbors, I'll put it in set T. Red indicates T. Okay, and their neighbors, I'll put it in S. T, the set of T's neighbors, I'll put it in S. Now S has these. Now T, the S's neighbors, I'll put it in. Yeah, getting it. So this is what two coloring is another way of seeing two coloring. Non-example would be like okay, and you pick an S, and its neighbors you put it in T, and their neighbors you put it in S, and then S's neighbors you put it in T. Okay, now T's neighbors you put it in S, and this guy belongs to T, right? This guy belongs to T, so its neighbor should be in S. So this guy I should be coloring blue. This I should put in S, and this person again is colored T, so his neighbor, this person, should be in S. So it's colored both red and blue. Okay, it is both in S, it is also in T. This cannot be made into a bipartite graph, because as you can see that starting from any arbitrary vertex, you should always be able to put it in two partitions such that of course this requires a proof, but I won't get into it. It should always be possible that as I'm doing this algorithm of putting it one partition or the other, I'm always following this sequence that does not disturb the bipartiteness. And at the end, suddenly it is not possible that I get a non-bipartite graph. Okay, but this is the algorithm. Okay, and is it clear? Vinod, is it clear? Suraj?
Yeah, it is clear.
Right. Okay. Suraj. Okay. Right. Okay. Yeah. Okay. I hope that it's clear for the rest also. Okay. But this is the algorithm, and how much time does it take? Right. We are more interested in the time complexity. This algorithm just takes one step for each vertex, and it takes around order n, which is linear, and so bipartite is in point. Good. So here's the final question. Okay. Tree is a set of all trees. A graph is a tree if it is connected and contains no cycles. Okay. So tree is the set of all those graphs that they are trees. So what is a tree? Connected. So we already saw what connected is. Okay. And next is no cycles. So for example, this is not a tree. This is a tree. This is not a tree. This is in fact called a forest. It is a union of multiple trees. Okay. And you want all these kind of graphs. So this is an interesting thing. So anyone has any idea on how to check whether it's true? Okay, Suraj already has one. Okay, DFS is cycle finding. Okay, DFS cycle finding and one connected component. Okay. Cycle finding using DFS, Suraj. Okay. So what you mean is, okay, I mean, given enough space, I think it's possible. Given polynomial amount of space, I think it's possible. So I think, Suraj, what you mean is, okay, Suraj's idea is as follows. So you have a graph, and I want to check whether um, it has any cycles or not. Okay. So what Suraj does is, you start from any vertex and start doing DFS. So you go to the deepest level, then come back, and then go to the deepest level, then come back, then go to the deepest level, and then come back, and then you encounter that I have reached a previous node without the backtracking. And then see, because this coming back is what is called backtracking, right? Not this one. This is called backtracking. And note that this branch did not backtrack yet. Okay. Because it kept exploring deeper and deeper, and we've encountered a node that is already visited. So we've actually found a cycle. Uh, right. So recall that previously, I think it was Vinod who suggested that, this cycle finding algorithm to locate triangles. Note that this cycle finding again, but using DFS, cycle finding again works actually, because we are not looking for a particular cycle here. Any cycle is fine. So we'll always locate them. Okay. And yes, good. Okay. This will form a DFS. This will do DFS. And finally, you want to check whether connected or not. Then DFS plus cycle check. This is to check whether there is a cycle or not. And secondly, it's check if one connected component. So if both are yes, okay, no cycle check. If both are yes, then output yes, otherwise. This is clear, right? And good. Now, does anyone have a suggestion on how to make this even more simpler, this part? By the way, this one, checking one connected component, this comes from question A, 1A. From 1A. Can we make this even simpler? Can we check for cycles without doing a DFS? Again. So this okay. Let's say we did it. This we are allowing. Okay. This we are allowing. 2 we are allowing. 1 I want to do it without using DFS. Is there a simple technique? Yeah, Rahul.
A tree can have n vertices and -1 edges.
Right. Good. Right. Note that, okay, in a tree, okay, with n vertices, and m edges, okay, m is exactly equal to n minus 1. But you need not know this exact fact. You can rather come up with your own observation as follows. Okay, if no cycles in a connected graph, then m is always less than n. Okay, I'll give you an example. For example, this is a set of vertices. I want to avoid cycles. Okay, and okay, there are 5 vertices here. I want to avoid cycles. I start distributing the edges. Let's say I put an edge here, then I put an edge here, then I put an edge here, then I put an edge here, okay, and then I put an edge here. So how many? 1, 2, 3, 4, 5. 1, and how many edges are there? 1, 2, 3, 4. Oh, okay. So I've already formed the cycle. What am I doing? Yeah. Note that now if I put an edge anywhere, I will always form a cycle. If I put an edge here, I formed a cycle. If I put an edge here, I form this huge cycle. If I put an edge here, I always form a cycle. Okay, this can be argued using pigeonhole principle. Okay, if you're aware, you can say that, oh, okay, if these vertices can be considered as pigeonholes and edges as pigeons, if everyone is familiar with pigeonhole principle, then you can say that, oh, okay, if I put n plus 1, okay, many pigeons in n minus 1 pigeonholes, then there will always be, a pair of vertices such that, there is an edge between them. You can make such an argument, but you can look at it intuitively also, that if I put an edge here, then obviously it will have a cycle when it is connected, mind you. I would ask you to look into the case why this is supposed to be connected. Okay, and therefore you can replace step 1. Okay, alternate to step 1 is simply check if the number of edges is less than the number of vertices. If this is true, then we output yes, provided we do step 2 also. Okay, good. So is it clear, everyone? Yes. Okay, good. Vinod and Rahul also, I think it's clear. And Syed and Pradeep, Mariam also. Please let me know if there are any questions. Okay. Okay. So those were some simple demonstrations. Okay. And okay. So we'll try to be more quicker. Okay. For the rest of the examples. So here's the question. Okay. Let L1 and L2 be two languages in NP, while L3 is a language in P. Which of the following is known to be true? Okay. So L1, L2 are in NP, and L3 is in P. Which of the following are known to be true? So, okay, I think this was explained in the lectures, at least A and B. So I'll just explain the first one. L1 union L2 is in NP. Okay, Suraj says 3, 1. Okay, and 3, 1 means A and C. So B and D are not in NP. You are saying
D is not in NP.
okay.
ABC are in.
Rahul says
ABC are true.
Okay, Rahul says ABC are true. Okay, good. So Suraj says C and D. C and D are not true. That is what you mean, Suraj? Right? C and D are true. Okay. C and D are true. Okay, let's see. Others also, if you have any guesses, any just check. Just let me know. Okay. So let's look at this. Okay. L1 union L2 is an NP. This happens to be true. Why this is true, I'll let you know. Since L1 is an NP and L2 is an NP, let's say L1 is an NP via a non-deterministic Turing machine M1, and L2 is an NP via a non-deterministic Turing machine M2. This follows from definition. If it is an NP, it means there is a non-deterministic Turing machine which runs in polynomial time, which solves the problem. Okay. Now I want to do the union. What is meant by union? L1 union L2 means all the strings that are in L1 and in L2. Okay, so how do I solve this? I just take a problem. If I take the machine M, okay, and I okay describe machine M as follows. On input X, okay, I run M1 on X, okay, and remember that M1 is a non-deterministic Turing machine. So it will start making some non-deterministic choices. And when does M1 accept? And it may have accept, reject, reject, accept, reject, and so on. And this time is polynomial, according by definition. Okay, this time is polynomial, and these may be exponential. The number of possible, computational paths. And when does M1 accept? When there is at least one path which will accept. Okay, and if there is a computation path, a non-deterministic computation path that accepts, then I simply accept. Then the entire machine M will accept and hold. Why? Because being in L1 is enough of a condition to be inside L1 union L2. Okay, and next, let's say M1 does not accept. Okay, if M1 does not accept, it means it is not in the language L1. Now I need to check whether it is in L2. Okay, how do I do that? I just run M2 on X. Okay, and this happens when all are reject. Let's say all of the paths reject. Now I run M2 on X. So I do this. I run M2, I run M2, I run M2 on all the paths, and then there could be accept, reject, reject, accept, and so on. And again, when does M2 accept? If at least one of the paths are accepting. Okay. Now, if again there exists computation path that accept, then M accepts and holds. Okay, this is just simple. Actually, to show for P also is the same idea. Okay, and then you just end and reject if both don't accept. Okay, so this is the idea, and for intersection, right?
That means we can make a bigger machine M, which takes two subroutines type M1 and M2, and pass
Right.
the same as
Right.
as any input instance of that problem. We pass both these machine M1 and M2. If either of these accept, then accept.
Good. Exactly. Now,
So this is the non-deterministic Turing machine.
This is non-deterministic Turing machine. That's right. So
yes.
M is non-deterministic Turing machine.
Yes.
Right. This is non-deterministic Turing machine. And why is it enough to show that it is NP? To show that it is an NP, I need a non-deterministic Turing machine that additionally runs in polynomial time. And this guy M1 ran in polynomial time, and this guy also ran in some polynomial prime time. Okay, both of them run in polynomial time. I am running them one after the other. So if I have a total time taken, will be first polynomial plus the second polynomial, right? Which is still polynomial.
Yes.
So I have come with a non-deterministic Turing machine M, which runs in polynomial time. So hence L1 union L2 is in NP.
Yes.
Okay, good. So I hope it's clear with everyone else. Now just tell me what kind of to do for L1 intersection L2. What kind of modification do I need to make? If I want to show
both
that
machine,
yeah,
if both machines accept yes,
exactly. If both machines,
then output of the bigger machine M is yes.
Then the output of the bigger machine is yes. Right. So it looks something like this. So M1 has several possible choices, and then it lands on accept, reject, and so on. And now, if M1 rejects in the beginning itself, it does not belong to M2. Okay, if all of them are reject, it does not belong to L1 at all. So we can stop checking because we are looking for intersection keys. Remember, so intersection means both of them must accept. So on one such computation path, if it is accept, then I run M2, and here too I run M2, and so on until I reach a node which is accept. And if this is fine, then I'll say yes. And this is the bigger machine M, and this again takes polynomial time, and this also takes polynomial time, and so the entire thing takes polynomial time. And this is a non-deterministic Turing machine. There are several branches, so this shows that L1 intersection L2 is in NP. Okay. Okay. Yeah, Said, do you have a question?
No, sir. I got it.
Okay, got it right. Okay, Vinod, are you able to hear? I saw you. I think there is some kind of internet connection at your end.
Yeah. Now it is
Now
audible.
it's fine.
I'm
Okay, sure. Okay, good. Just let me know if you want to repeat. If you want me to repeat anything. Okay. So both are fine, right? So yeah. Okay. So L3 bar is in P. L3 complement. Okay. L3 bar is in P. So I think wait, Suraj had said that this is not in P. No, this is false, I think. Oh, sorry. Here Suraj had said this is true. Okay. Okay. Good. Right. And Rahul also. Yeah, this is true. L3 bar is in P. Okay. And by the way, there was an assumption here that L3 is a language in P. Okay. So not just this. L3 bar is in P, where. Okay, wait. I'll rewrite this. If L3 is in P, then L3 bar is in P. This is what they are saying, and the answer is simple. So can you? Okay, I'll just give an additional hint that L3 is nothing but all the strings that do not belong to L3. L3 bar is all the strings that do not belong to L3. And remember that L3 has a polynomial time deterministic Turing machine because it is in P. So can you tell how I can come up with a P algorithm?
Is that a statement is correct?
Yeah.
Is that a statement is correct? L3 belongs to P. That is L3 bar belongs to P2.
L3. Okay. Yeah. Okay. Why is this correct? Oh, this statement is correct. That's what I'm saying. This is what you meant. This is the question, right?
Okay, I got it.
This is true. That is what I was saying. Right? Seth, is that fine? And I'm giving the proof for that. I'm giving the solution for that. Okay? And you can see why this is correct, right? This L3 bar is the complement of that set.
Complement of the Turing machine of L3.
No, not the complement of the Turing machine. Complement of the
Because
language.
L3 belongs to P. L3 belongs to P.
Right.
Okay. So there exists a Turing machine.
Right.
Okay. So I am on any input stance, it will give you yes or no.
Right.
There are two answers.
Right.
Okay.
Oh, okay. By the complement of it. Okay. You meant that. Okay. Yeah. Good. That's right.
So on the answer of the previous machine, yes. Now this new machine is going to answer no. In that terms.
Right. That's right. Yeah. Okay. Sorry. By complement of the Turing machine, I thought you meant the disk. This L3 means
No.
the set of Turing. Okay. So you mean the complemented answers of the Turing machine?
Yes,
Right?
yes.
Okay, right, good. So yeah, so here's the simple. Um, let's say L3 is in, suppose L3 is in P via a Turing machine, deterministic Turing machine, M3, let's call it. Okay, M3 runs in polynomial time, running in some polynomial time. Okay, now here is an algorithm. Okay, here is a Turing machine, deterministic Turing machine, M3 prime, let me call it, and on input X, okay, simply run M3, okay, on X. If M3 says yes, output no. M3 says no, I output yes. Okay. And why does this work? If M3 says yes, what does it mean? X belongs to L3. Output no. Why? Because X belongs to L3 is as good as saying X belongs does not belong to L3 bar, the complement of the set, right? And M3 says no, which is X does not belong to L3, because remember M3 is deciding the language L3. Okay, this is as good as saying X belongs to L3 bar. So our output says no when X does not belong to L3 bar, and yes when X belongs to L3 bar. We have that M3 prime, this machine M3 prime decides or computes the language L3 bar. And how much time does it take? Time taken is how much ever time M3 takes plus some constant time for step 2. Okay, which is polynomial on the size of the n. Clear, everyone? Right?
Yes.
Okay, good. Okay. Sure. Sayed, is
Excuse
it
me,
clear?
sir.
Yeah, go on.
So can you go back to little upper side?
Go back
That
to,
if statement, if statement,
okay, if statement. Okay. Do you mean this if statement?
not if, not this one.
Okay. This one.
Not
No, no.
not after
In the
this. The statement L3
Oh,
in the hypothesis,
and L3
L3 is
component.
okay.
Yes, this one.
This one.
If L3 belongs to P. That is
hypothesis is
L3.
L3 belongs to P.
P
Then
that
conclusion is
belongs to P.
L3 belongs to P. This one. This entire
If
statement. You
this
mean?
is true, if this is true,
Yeah.
then the one, the second one, if M3 says yes, that is output no.
Huh.
I didn't understand these two
Oh,
statements.
okay. Sure, no problem. Okay. So what we are doing is, okay. Said what we are doing is we are with okay. So what we are doing is, okay. We want to show that. Firstly, what do we want to show? We want to show that L3 bar is in P. Okay. And how to do that? By definition of P, come up with a deterministic Turing machine, which I'm calling M3 prime, okay, running in polynomial time. Okay, this is the aim. This much is clear, right? How to show L3 bar is in P.
Yes.
Yeah, okay, good. Now, L3 is in P by assumption, by the question itself. This is known to us. Okay. Now, what is L3 bar? L3 bar is the nothing but the bigger set. Okay, this is the set of all strings, which is called sigma star 0 1 star. Okay, and here there is L3 setting. Okay, and L3 bar is this set, which is outside L3. Okay, which is nothing but sigma star minus L3, the universe minus whatever is in L3, right?
Okay.
Okay, now this can echo, since any string I take will always be in sigma star. I can always write L3 bar as the set of those strings that simply don't belong to L3, because my whatever string I talk about will always be in this place. Okay, so if I say this shaded area, I mean only those strings that don't belong to L3. Okay, I can write this as the definition of L3 bar. Okay, L3 bar is the complement of the set, which means all those strings that don't belong to
Okay,
L3.
okay, I got it.
Okay, got it right. Now, 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 L3 is in P, which means there is a deterministic Turing machine running in polynomial time that solves L3. What do I mean it solves L3? It can check if X belongs to L3 or not. Given any string, it checks whether it belongs to the problem or language L3 or not. Okay, by definition of L3 being in P, I have a polynomial time algorithm or a polynomial time Turing machine to check whether a string belongs to L3 or not. Okay.
Okay.
Okay. Now, look at our objective again. Come up with a deterministic Turing machine M3 prime, which runs in polynomial time, that decides, okay, that computes L3 bar. We want to check. We know how to check now. Now we know how to check whether X belongs to L3 or not. We want to check if X does not belong to L3 or not. You can see, right? Because X does not belong to L3 or not is same as saying X belongs to L3 bar or not.
Mm-hmm.
Right. So here is the algorithm. I simply take the algorithm for L3, okay, and take any string, okay, that I need to test. You give me a string X, and I will run that algorithm. I'll run that algorithm for L3, okay, and if L3 says yes, the string belongs to me. Okay, sorry. If M3 says yes, the string belongs to L3. Then I need to say no. Why? Because if it said yes, then it belongs to L3, which means it does not belong to L3 path. Okay. Algorithm for M3 prime is as follows on input X. Remember, M3 prime is supposed to decide L3 bar. Okay. L3 bar means whether it is not contained in L3 or not. Okay. So what I do is I run the algorithm. Okay. I run, let's say this is M. Okay. M decides whether X is in L3 or not. Run M on X. Okay. If M said yes, then output no. If M said no, then output yes. Now I'll tell you why exactly. Okay. Now here's the proof for this. Okay. Let's say I give you an input X and it belongs to the language L3. Okay. Let's say this is the first case. You give me a X, okay, and it is in L3. Then What's wrong? One moment. I hope it's not gone. Okay, yeah, it's not gone. So you give me an x which belongs to L3. If it belongs to L3 and I know M decides it, okay, then M, what does M do? Outputs yes on X. If you give, because M is the algorithm that solves L3, it says yes on X, right? And at the same time, if X is in L3, what does it mean? X is in, not in L3 bar. That is what we found out right before. And if it said M outputs yes on X, okay, then what did it say? We output no. And secondly, if X is not in L3, what does it mean? It means X is in L3 bar, right? And what does it mean if X is not in L3? It means M outputs no when given X. So what does M prime 3 do? M prime 3 outputs yes. Now this part, X is not in L3 bar, then what did we output? We outputted no. If X is in L3 bar, what did we output? We outputted yes. Okay. Now I hope you can see that what does M prime do? What does M prime do? It solves language L3 bar. It can tell you this new M3 bar, M3 prime will tell you exactly whether it belongs to L3 bar or not. Right? This new algorithm, if it gives you X, if you give me X, you running this algorithm, I'll tell you, oh, okay, it outputs. If it belongs to my language, I'll say yes. If it belongs to my language, I'll say yes. If it does not belong, I'll say no. How did we do it? We just flip the answers from its complement language. Is it clear, Sayed?
Yeah, okay, I got it.
Okay, good. Okay, now, okay, this is true. Now, what is the only question left? Whether L1 bar is an NP or not. Okay. L1 bar is an LP or NP or not? Yeah, Rahul?
No, it is not.
Okay.
If it is in NP and it is in complement of this is also in NP, then it will be in P.
So you mean L1 bar is in P?
No.
Then?
The assumption was that L1 belongs to NP.
Yeah, L1 belongs to NP. Assumption.
That was the assumption, I think.
Right.
Okay. If the complement of L1 is also in NP, then L1 must be in P.
There's a complement of. Oh, okay. If the
NP
complement
and
of.
co-NP.
Okay. It must be in P. Okay.
And
Right. That is a. Okay, that is an interesting statement. What you mean is that if L1 is in NP, then L1 is in P, then L1 is in. Oh, what am I saying?
complement of it.
Sorry, if both are in NP, right? If both are in NP, then L1 is in P. Okay. Yeah. This is what you mean, no?
It might be chance. But there is NP intermediate also.
Okay. Okay.
Graph isomorphism, I think.
Right. Graph isomorphism. Okay. I'll come to it. Okay. But but this statement is actually not true. Okay. yet. I mean, we
Is
don't
that
know.
that I said that it was false?
Right. What you said, okay, is it's not that it's not false. It is not true as of now. No one has
Yeah.
come up with a proof for this. Okay. That's why the question
Okay.
actually,
So
yeah,
that means
says
you are
no.
trying to say that the proof doesn't exist.
The proof has not existed yet.
Okay.
And probably could not, maybe it does not exist. Okay. But that is a philosophical point of view. But, but it has not
So,
existed yet. Okay.
so it is a conjecture or whatever it is.
Yeah, it is a conjecture that way that if you know L1 is in yeah, if this is true, if both are in NP, then L1 is in P. What this
Yes.
means is, okay, so yeah, why I put this question is exactly because of this, that you know the it is to define this set, okay, this class, okay, called co-NP. You may see it, you may have seen it in the week 2 lectures, okay, co-NP. Which is all the set of strings, all the which is all the set of languages. Note that this is not a language. Okay, CoNP is a class of languages, so it contains languages. It contains all those languages such that their complement is an NP. Okay. Note that this is not the same as NP complement. Okay, this something like this makes little sense. Okay, it is take all the languages in NP. Now just take for each language take its complement. Now those form a class called CoNP, okay, which is another very rich class, and we'll actually see it later. I have a question on this, but P is contained in NP intersection CoNP. P is
Yes.
not belongs to contained in NP intersection CoNP. So
Yeah, it is a subset.
right.
But this set itself is not equal to P. The problem is that
Exactly.
the equality.
Exactly. This is NP. This is co-NP, and this is P, and this is NP intersection co-NP. And if like what Rahul said, okay, if you are able to prove this conjecture, okay, that L1 is in NP and L1 bar is in NP, which simply means that L1 is in co-NP, which simply means that um, L1 is in NP intersection co-NP. Okay. And if it is true that L1 is in NP intersection co-NP, and then L1 belongs to P, then this is a huge result. Okay. No one has been able to prove this yet. And this will be a very interesting result. And popular belief is that this is not true. Okay. And that there are, languages that sit here which are not in P.
That is graph isomorphism, I think.
No. Graph isomorphism is NP intermediate, I agree, but it is not shown to be in NP intersection point. NP complete is here. Graph isomorphism is here. Okay. So, yeah. But the NP intersection co-NP is an interesting class of problems. The from a very philosophical viewpoint. So
But subgraph isomorphism is NPC.
Subgraph isomorphism is
NPC.
yeah, right. That's right. Okay. But yeah. Anyway, so this is not known to be true. But the another reason why I wanted to include this is because this idea of flipping the yes and no will not work. Okay, and I'll just quickly demonstrate. Okay, so here was M3 bar, M3 prime, and here was the machine M3. Okay, and if M3 said yes, I say no. If M3 says no, I say yes. Okay, and here's the input x, and I just pass it to M3. And this was the idea. If I use the same idea for NP, okay, before, remember, the machine was non-deterministic, it will not work. Okay, how much time do I? Okay, so the idea is that if I start my non-deterministic Turing, this time it's non-deterministic, okay, because this, in this question, I'm saying L1 bar is an NP, right? I want to decide an L1 bar using the same idea. So I'll run M1, which is a non-deterministic Turing machine, deciding L1. Okay, and this makes several non-deterministic choices, and here I come up with, accept, reject, reject, accept, and so on. And if it accepts, then I'll say reject, and if it says reject, then I'll say accept, right? So I'll say reject here, I'll say accept here, I'll say accept here, I'll say reject here, I'll say reject here. Okay, now does this decide L1 bar? That is the question. Does this decide L1 bar? That is the question. Suppose X is in L1. Okay, and this is the computational graph for it. Okay, and on some paths it accepts, some paths it rejects. And this bigger machine is my M prime. Okay, M1 prime. This bigger machine, which is supposed to decide L1 bar. I just complemented the output. So if X is in L1, fine, it is in L1. I want to show that it's not in L1 bar, right? And okay, sorry. Let's say this case, X is not in L1 bar. Okay, there is. Okay, yeah. So let's say X is in L1 bar. Sorry again. So there is at least one path where it accepts, and let's say there is another path where it accepts. There is some path where it rejects. Okay. Once I flip it and make this M1, there is reject also, there is accept also, there is reject also, and so on. Now, this bigger machine M1 prime, if given X for this computational graph, what will it do? Will it accept or reject? If this is the behavior, some of the paths accept, some of them reject. This bigger machine, according to the definition of non-deterministic Turing machines, will it accept or reject? So this is what I get. Some of the paths reject, some of the paths accept. So is this machine supposed to accept or reject? By definition. Okay. Okay. So by definition, a non-deterministic Turing machine accepts if there is at least one path which leads to accept. As I told earlier, it is a very lucky guesser. Okay. So even if one path accepts, then it is supposed to accept. Then M1 prime accepts. But if M1 prime accepts, what does it indicate? This indicates that X belongs to L1 bar also, which is not possible, because it cannot belong to L1 and not belong to L1 at the same time, because this simply means that X does not belong to L1. There's a contradiction here, clear contradiction. So you can see that the previous logic does not hold. Simply flipping yes and no will not work here because of non-determinism. Okay, is this clear, Rahul?
X
Hello?
belongs to else if at least one of the path of M1 accepts.
Yeah. Now what I'm doing is
then-
yeah.
and M1 complement also accepts
Right.
on at least one of the path of the M1 which accepts,
Right.
M1 complement also accepts.
Right.
How?
Okay. How? Because.
Because it is the complement of the previous machine M1 itself.
Right. 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 Suraj says, "Sir, can you explain in short again?" Okay. Yeah, Rahul. I'll explain once again. Okay. But see, I'm not claiming that this algorithm works. Okay. I'm not claiming that this algorithm decides L1 bar. I'm saying this algorithm does not decide L1 bar exactly because of this problem.
Decides, that means it is a decider.
It is a decider, which means, yeah, it computes, or it, yeah. Okay. Okay. So yeah, here, look into it once again. Previously, what we are doing, uh, L1 is computed via machine M1. Okay. Before it was a P machine. Now it is an NP machine. Okay. Before it was a P machine. So what did I do? I just ran the machine M1. If it said yes, I'll say no. If it said no, I'll say yes, and I'm done. Now it's tricky. If I use the same algorithm, okay, I'll use the same algorithm here. So what is the algorithm? M1 prime. Okay. This is the algorithm. And I'm using the terms algorithm and Turing machines interchangeably. That does not matter. Okay. So here's what first happens. Okay. What is the algorithm? Run M1 on X, but remember this time it is non-deterministically, because M1 is a non-deterministic Turing machine. I'm trying to create another non-deterministic Turing machine that to show is what do I want to show, that M1 prime decides or computes L1 bar. Okay, this is what I want to do, and I'll use the same logic. Okay, if M1 says no, output yes. If it says yes, then output no. Okay, this was my algorithm. Previously also this was the algorithm. The only difference is this, right? It is non-deterministic now. So now this is a game changer. Why? Because here I run M1. Okay, this is my new machine M1 prime. Here I run M1 on X, and it will start making some non-deterministic choices. Right, it will start branching off into several choices, and of course it takes polynomial time. Time is not a problem. Okay, time is not a problem. It still takes polynomial time, but at the end, some of the paths accept, and some of the paths reject. Maybe in the middle it rejected, and so on. Okay. Now, what does this mean that some of the paths accepted? It clearly means that X belongs to the language, right? Because even if there is one particular computation path where it accepts, we are good, right? X accepts. Sorry, what am I saying? M M1 accepts X. Why? Because there exists at least one computation path that leads to accept. Okay, so M1 will clearly accept. If M1 accepts, what does it mean? If M1 accepts and M1 decides L1, it means that X belongs to the language L1. Right? Right?
Yes.
Or the other way around. Yeah. If X belongs to L1, then M1 will have at least one accepting path.
Fine.
Fine. Now let's say it had a combination of accepting and rejecting paths like this. There is accepting and rejecting paths. Now, by step 2, If M1 says no, then we are supposed to output yes. If it says yes, output no. If it says accept, I'm supposed to reject. If it says reject, I'm supposed to accept. If it says accept, I'm supposed to reject. If it says reject, I'm supposed to accept. This is what is happening. Getting it?
Yes, yes.
Right. Suraj, is it clear?
We are complementing the output.
Complement of L1,
Yeah.
right?
Complement of the algorithm. Exactly.
Okay.
Yeah. Now is the key part. Look at this algorithm M1 prime. It is a non-deterministic Turing machine, non-deterministic algorithm. And this is the computation path of the non-deterministic algorithm M1 prime, the bigger algorithm, which does the flipping, which does the complement. Given this kind of a behavior, where at the end it has several accepts and several rejects, what does it do? Does it reject or accept? At the end, let's say this is yeah.
Can you repeat again?
Yeah, this M1 prime, which is the bigger, Suraj, but this which is the bigger algorithm, okay, and it has several computation paths where some of the paths reject, some of them accept, okay, and what does this machine M1 prime choose to do? Does it choose to accept or does it choose to reject that particular X? By the behavior of non-deterministic Turing machines. When do non-deterministic Turing machines accept? This is the condition.
There is
right?
at least.
Exactly. There is at least one computation path that leads to accept.
Yes.
Right. Sayed, is it clear? That is the definition of non-deterministic Turing machines. How they accept. Right. Hello?
At least there exists a path.
Right.
One accepting.
Accepting path. Yeah. Suraj also it's clear, right? Yeah, accept. That's right. So again to repeat, said there are several accepts and rejects here. But since there is at least one accept here, there are three accepts here, in fact. There could be more, let's say. My machine M1 prime chooses to accept because that's how non-deterministic Turing machines are designed to work. If there is at least one guess where it accepts, then the entire machine will accept. Okay, good. So if M1 prime chooses to accept, then it chooses to accept. What does it mean if M1 prime is supposed to decide L1 bar, right? If M1 prime chooses to accept, what does it mean? It means X belongs to L1 bar because it has accepted and M1 prime is supposed to decide L1 bar. Right? Mm-hmm. Now, if X is in L1 bar, what does it mean? X does not belong to L1.
Fine.
Now, there is a contradiction here. Right. So this algorithm is not correct. It causes this problem. M1 prime is not correctly able to decide L1 bar using the same flipping logic. Right. Okay. This is why M1 prime is not a correct algorithm to decide L1 bar. So we don't have an NP algorithm for. So no, not an NP algorithm for deciding L1 bar. So in fact, like Rahul pointed out, this is an open problem. This is a huge problem, in fact. This is a very, very difficult problem in complexity theory, which is not known as of now. There have been hundreds and thousands of attempts, okay, and yet we do not know the answer to this. So you saw the simple algorithm of just flipping. Okay, simple algorithm of flipping. If we bring it to the non-deterministic setting, does not work. We probably need much more complicated techniques to actually design an algorithm that will actually show that NP is equal to CoNP. Okay, yeah, this algorithm. I mean, if you, let's say, come up with an algorithm, you'll end up showing that NP is equal to CoNP. Any language in NP, if you complement it and you still have an NP algorithm for it, then you simply that simply means that the complement of that NP language is in CoNP, and you know that any language in CoNP can be decided by an NP machine, which means CoNP is equal to NP. This, if you show, then yeah, I mean, you'll be pretty famous. Okay, Said, is it fine?
Yes, I think so.
Okay. Okay, so but we can discuss at the end. Okay, Seth, if you have if it's still not clear, we can discuss at the end of the session. Okay.
Okay.
Okay, sure.
I
But
got this, but I have a question about that. How this is not correct? Like x belongs to L1.
right. Okay, okay.
Contradiction I didn't understand. Okay.
Sure. We'll come back to it at the end then. Okay. Okay.
Okay.
Okay. Great. Um. Okay. The rest, I hope it's fine, right? Mariam, Suraj, Rahul, and okay. Let's quickly try to finish the other questions. So I think all of them we cannot do, but okay, I'll do the interesting ones. Okay.
Is there any possibility that this question should be shared before the session so that we can go through once?
Okay, I could possibly do that, but some of the times I kind of add few questions at the last moment, so all of them may not be there. But I
Like
could,
some of them.
yeah, some of them I could share it in the forum. Furthermore, what I can do is I can post these. I can. I'll always upload them to a Google Drive. Okay, that will be known to you. So, okay, along
Okay,
with
okay.
so this will be in the Google Drive. Furthermore, what you can do is you can take a look at these questions, and in the next session, next Tuesday, when you come, you can ask. We can discuss. Okay,
Yes, yes.
that too we can do. Okay, good. So. Yeah, so let's look at this problem. This is quite interesting. Okay, it's simple but quite interesting. So recall SAT. Okay, the problem of checking whether a formula has at least one satisfying assignment. Define the problem double SAT as follows. Double SAT is all the formulas with at least two satisfying assignments. Show that double SAT is NP complete. Okay, let me recall once. What is a reduction? Okay, before, just let me quickly recall what a reduction is. Okay, reduction L1 polynomially many one reduces to L2. Okay, if there exists a sigma, okay, or f, whichever was used in the lecture, which is a function which takes in a string and gives you another string. Well, it is a way to solve problems. Okay, it is a tool to solve problems, and such that for any x, okay, if x is in the first set L1, if and only if sigma of x is in L2. So sigma is actually a transformer. This is what the reduction actually is. Okay, and furthermore, sigma can be computed in polynomial time. In polynomial time. Okay, and a nice way to see it is if I want to come up with one algorithm to solve another algorithm. Okay, for example, here is algorithm for L1. and it uses as a subroutine an algorithm for L2, and I take the input to algorithm L1, which is an X, and pass it through sigma, and then I give sigma X to algorithm 2. If algorithm 2 says yes, then I says yes. If an algorithm says no, if L2 says no, then I say no. This is what is actually happening. If it is in L1, sigma of X is in L2. If it is, because it's an if and only if it is not in L1, then sigma of X is not in L2. And sigma can be computed in polynomial time. This guy can be done in polynomial time. Now, why is this interesting? Because if L2 can be shown to be in P, then L1 can also be shown to be in P. Okay, you may have seen it in the lectures. I'm just quickly going through, because how to come up with an algorithm for L1. I'll simply compute sigma of X. Given X, I'll just compute sigma of X and run P algorithm for L2 on sigma of X. And if yes, then output yes. If no, then output no. So you can see that on solving L2, I can always get L1, and it is important because I'm coming up with a polynomial time algorithm for L2. It is important for this to happen. It is important that this should be done in polynomial time. Sigma should be computable in polynomial time. Okay, and therefore, since if I can solve L2, then I can solve L1. But it is not sure whether if I can solve L1, then I can solve L2. It is not two ways. It's not a symmetric relation. Okay, and so in essence, it shows that L2 is possibly harder than L1, because if I solve L2, I can solve L1 also. So therefore, this greater than equal to sign says that whatever is to the right is harder than what is to the left, harder or as hard. Okay.
So L2 is at least as hard as L1.
Exactly. L2 is at least as hard as L1.
So if L2 is solved in polynomial time, then we can solve L1 also.
You can also solve L1 using this logic. Compute sigma,
Yes.
just simply give sigma. And this algorithm runs in polynomial time. Okay. If this is not clear, please check out the lectures once. Okay. It's clearly mentioned out there. And but we can discuss at the end also if you still have any doubts. And another notion is of completeness. Okay. Now, what is completeness? So we said that okay, L2 is at least as hard as L1, and let's say L1 belongs to something like NP. Can I come up with a language which is like the hardest language in NP? Okay, can I come up with a language which is the hardest language in NP? That is, given any L1, L2, which is NP complete, say, okay, sorry, which is that hardest language. Why is it
Every
hardest? So
problem
that,
in NP must be reducible in that problem.
right.
Every problem in that class, or
Right.
say NP, or whatever it is class, XYZ,
Exactly.
that must be reducible in that.
Right. That's what I'm coming to. So so I want, if I have the set NP, okay, I want to come up with a candidate such that this is harder, okay, than possibly everything else, at least as hard as everything else. Okay, and this is what is called an NP complete language. And it's not just a single language, there are several languages, as you may have seen. And so formally it is for all languages, say B in NP, B reduces to polynomial many 1 reduces to A, okay, then A is an NP complete language. Now, why is this interesting? Why is it interesting? If A, any NP complete languages, is shown to be in P, if you can come up with a polynomial time algorithm, then you show that since everything can be, everything reduces to this, and we saw that reduction means that if A is in P, then B is also in P. Okay. If A is in P, then B is also in P. And if A is NP complete and everything reduces to it, then if A is in P, then everything is in P. Everything in NP is in P, which means that P is equal to. This is why one of the reasons why NP complete languages are
That
special.
function, that reduction function is bijective, sorry, invertible.
That function is invertible. No,
Invertible.
that is not clear.
That is
That is not clear.
because problem, every instance of B is going to be reduced in A or mapped
Right.
in A. Sorry. Okay. So if A belongs to P, that means there exists a deterministic definition that A can be solved. With the same invertible function, can I map all the problem instances in A to the B?
Right. So yeah, Rahul, that is another huge problem that is studied, which is what are called isomorphic reductions. You can check it out later on. And there is a maybe function is not invertible. Yeah, right, Suraj. So because let's say I have an A, okay, which is in language L1, and I have a L2, okay, which is in B. Sorry, I have L2, which has, let's say, okay, so this is a string. Okay, these are strings X, Y, Z, and there are strings A, B. Okay, and suppose I have a reduction sigma which takes X to A and which takes Y to B, and let's say Z is taken to A again. Okay, Rahul. So now I have this problem that sigma X is equal to A and sigma of Z equals to A. Now, if I want to invert this, let's say I'm given A.
Okay, so there may be some instances in L2 that is not the
yeah,
doesn't
exactly.
have the pre-match. Okay.
Exactly. There may not be pre-match. I think Suraj's comment was exactly that only, that the function may not be invertible, right?
Okay.
And but it's a good question, because this is why the reduction is called a many one reduction, because the function itself is a many one function. Okay, this M comes from many one.
Yes.
Okay, and just a quick offshoot. It's since it's quite interesting that now a good question is whether you can come up with these invertible, um, invertible.
Because the doubt is that if A is soluble with P, that means A belongs to P. So that means there must that B is also solvable in P.
No, that is not clear. Why the other way around should happen? Because
No.
Yeah.
So, can you bring down the slide?
Bring down the slide like this.
Yeah. As you have written that B is polynomial time reducible to A.
Right.
Okay, and if A is solvable in P, then B is also solvable in P.
B is solvable in B.
A is solvable in P. That means A belongs to P.
What does it mean for A to belong to B? Because A is a set, B is a set. A is a set of strings, B is a set of strings. A cannot belong to B, right?
A belongs to P. Polynomial.
P, okay, polynomial. Set okay, P. Sorry. Yeah. So if okay. So A belongs to P, then B belongs to P.
Yeah.
Right.
So that is what the doubt comes from. So if A belongs to P, that means by the same reduction function, I can also solve with the P also.
Exactly. If it was invertible.
Yes.
If it was invertible. Good. Yeah. Right. So question is, to be invertible, it is what is called the sets needs to be what is called isomorphic. Okay, but this you need not know. But a good question is whether all NP complete languages are isomorphic. Okay, that is invertible. There are invertible reductions among the NP complete languages, because NP complete languages, they reduce to each other because they are anyway in NP, right? So this is a famous conjecture which is called the Borman-Hartmanis conjecture, which is not proved or disproved until now. And popular belief is that it is not true, that they are not isomorphic. Okay, that you cannot come up with invertible reductions for NP complete languages. Okay,
Okay.
so you can look into this Borman-Hartmanis conjecture. A lot of work has been done here. Okay, and but good question. Yeah. So yeah, let's quickly look at this. Okay, I'm running out of time. Uh, okay, so SAT, okay, is an NP complete language. Anything reduces to SAT. You may have seen it in the lectures. What is SAT? Given a formula, and it can be thought of as OR and AND gates. Okay, that does not have a cycle, which means I cannot have a gate feeding into two different. So such a cycle cannot exist. Okay, so this is a formula. This is an example of a formula. I can even write it as a single expression. Can I give it an assignment? Let's say x1, x2, x3, and so on till xn. Can I give it an assignment 0, 1, 1, 0, and so on? And there could be negation gates also, such that this will finally output 1. This is the question. Okay. And even if there exists one particular assignment where the circuit is satisfiable, which means the circuit will give a 1, then I'll say that the formula or the circuit belongs to a SAT. Phi belongs to SAT if and only if phi has at least one satisfying assignment. If no assignment satisfies, then obviously it is not in SAT. Okay. Now I'm slightly changing it. I'm saying double SAT. Phi is a formula with at least two satisfying assignments. There needs to be two satisfying assignments. Okay. So phi is in double SAT if and only if phi has at least two satisfying assignments. Okay, at least two satisfying assignments. And problem is show double SAT is NP complete. Okay. Now, how do I do that? One of the most popular techniques to do it is using reductions. Solution is reduce the SAT problem to the double SAT problem. Okay. Reduce the SAT problem to the double SAT problem. So, okay, now listen to this clearly. What does it mean? That is, what do we need to show? We need to show that there exists a transformation sigma, okay, which takes in a function, takes in a formula phi and produces another phi prime such that if phi is satisfiable, if and only if phi prime, okay, what is phi prime? Phi prime, which is nothing but whatever sigma gives on phi is in double SAT. Okay. And in English, what does it mean? That phi has at least one satisfying assignment if and only if phi prime has at least two satisfying assignments. Okay. So the problem is clear, right? Everyone, is the problem clear? I want to reduce the SAT problem to the double SAT problem. I want to come up with such a transformation that takes in a formula, okay, and if it is satisfiable, then the resulting formula, the new formula that I create, should have at least two satisfying assignments. And if it does not have at least two satisfying assignments, then the formula that I started with should not have any satisfying assignments. Clear? In other words, if I solve double SAT, I'll be able to solve SAT. Okay, this may not be immediately clear to you in the first glance. Okay, but once you are familiar with reductions, okay, that's what I want to that is what I want to keep as an objective, that you are more familiar with reductions. Okay, so if you see this particular problem, then you may be more comfortable with reductions later on. Okay, but yeah, if you have a formula which is satisfiable, then I want to come up with another formula which has at least two satisfying assignments. That's why it's called double SAT. Okay. Just to be clear, I'll give you an example of a satisfiable formula. Okay. For example, if it's x1 x2 x1 bar x2. Okay, this is satisfiable. Why? Because if I set x1 equals 0 and x2 equals 1, then what do you have? Then you have x1 is 0, x2 is 1, x1 bar is 1, this is 1, this becomes 1, this also becomes 1, and finally I'll get a 1. Okay, so this is a satisfying assignment. So what does it mean? This formula phi is in SAT. It has a satisfying assignment. Is it in double SAT? Can I come up with another satisfying assignment? Well, if I set x1
is equal to 1 and x2 is equal to 0.
No.
No.
Yeah. No, that will not work probably. So what did you say? X1?
x1 1, x2 0.
X2 is 0. So x1 1, this means it will be 1 here, this will be 0 here, and 0 here, and this will be 0. So no, this will finally give us 0. So this will not work. So but what will work is I think if x2 is 0 and x1 is no, x2 should be 1 anyhow. X2 is 1 and x1 is 1. Yeah, if both are 1, then it will work. So if both are 1, then this will become 0, this will become 1, and this will become 1, this will become 1, and this will become 1. Right? x2 equals 1, x1 equals 0. x2 equals 1, x1 equals 0. Yeah, Suraj, this is the same thing, right? This one. Right. That's right. x1 equals 0, x2 is 1. Okay. Now, there are two satisfying assignments. Second satisfying assignments. Therefore, phi is also in double SAT. Okay. I have 5 minutes. Okay. Now, okay, good. Now, with a single satisfying assignment, I want to come up with I want to transform it into a formula which has two satisfying assignments. Okay. So what do I do? Anyone has any suggestions? Okay. So if let's say phi has two satisfying assignments, then if I pass phi to double SAT, I don't have a problem. This also anyway has two satisfying assignment. It belongs to SAT, and this will obviously belong to double SAT. It is not a problem. It already has two satisfying assignments, and that is enough for me. Problem is when phi has exactly one satisfying assignment. Then I want to convert it to an instance of double SAT. I want to transform it. Okay, I want to transform it into a phi prime which has at least two satisfying assignments. Okay, anyone has any idea?
At least one of the variable of the exactly one satisfying assignment must be the same.
At least one. Okay, okay. I can even keep all of them same. I have no problem with that. Yeah, at least one should be same. I agree, because even if one of the variables is not same, then our function does not depend
Yeah.
on the input at all.
And rest of the variables can be flipped. On which
Rest of the variables can be flipped. You mean do a negation?
no, not
So let's say our file looks like this, and or okay, and let's say it looks like this: x1, x2, x3, x4, x5, x1 again. Oh, that is allowed. Yeah, that's allowed in a formula. X3, x5. Okay, but I think I'm going to leave it at that. I would like you guys to think on how to modify this. Okay, I'll just give you one hint. Keep this formula as it is. Add more gates here. Add some more gates here or some more inputs here, and then transform the formula into such a way, okay, such that if I have one satisfying assignment for this, then I'll have at least two satisfying assignments for this. Think about it. Okay, I'll do it first thing in the next session. Okay, so the next session will be on Tuesday, 6 p.m. and walk through these questions once again. Okay, this is quite an abstract field, but it is equally rewarding also. Okay, it's quite a beautiful field, and I hope you guys enjoyed this session. Okay, and I think we can wrap up. I'll just have a quick chat with Seth on that particular question, and then and the rest of you are free to leave. Okay, if you have any more questions, just let me know. The rest are fine. Suraj, Mariam, and Rahul.
yes, yes.
Yes, right? Okay. Okay, good. Suraj, fine, right? Okay. We'll meet on Tuesday, 6 p.m. then. Okay. This content will be uploaded on Google Drive as well as YouTube.
Fine.
Okay, then. Thank you. Okay. Yes, sir. Okay. Okay, thank you, Suraj. Okay. Good night. Sure. Okay. Syed, are you there?
Yes.
Yes, yeah. Let's
Yes, I'm
just
here.
quickly get through that. Okay, go through that. Which question was it? It was on the complementing NP, right? This one.
Yes, the contradiction one.
Right, right, right. So remember, okay, again, remember the previous algorithm for P. We showed that if I have a language, okay, and I can also, which is in P, okay, which has a polynomial time algorithm, I can always have another polynomial time algorithm which will decide its complement, which will decide if I can tell if it is there or not. Okay, if X belongs to the language or not, I can always tell whether X does not belong to the language or not by simply flipping yes and no.
Mm-hmm.
Okay, now what I'm doing here is, now we have a non-deterministic machine. Okay, how does a non-deterministic machine work? Okay, for a non-deterministic machine, if M is a machine, I can have several non-deterministic choices. I make guesses on the way. Okay, I make guesses on the way. I toss some few coins on the way, whether to move or left or right, whether it is head or tails. Okay, and if I have even one guess, non-deterministic guess, where I get an except, okay, where I get an accept. You may remember non-deterministic DFAs, right? Deterministic finite automata.
Yes.
Yeah, right. Even if you remember in the DFA, even if there is one path which lands on the final state, okay, on the same
Uh-huh.
string, I am supposed to accept, right?
Hmm.
Even though
This
maybe
one is the accept.
exactly. So similarly, we if even if one, so these accepts are your final states, and rejects are your non-final states.
Hmm.
Suppose then in the non-deterministic tuning machine, it works this way that even if one path on that particular string lands on an accept, then I'll accept.
Hmm.
Okay, then I'll accept. That much is clear.
Hmm.
Okay. So what is this machine going to say at the end? Even if one path lands on accept, yes, one path lands on accept. So this machine is going to say yes, right? Because there is at least one path that accepts.
Hmm.
Because there is at least one path that leads to accept.
Yes.
Then the entire machine will accept by definition.
Hmm.
Right.
Okay.
By this definition, even if one path accepts, as you can clearly see here, one path accepts here, so the whole machine will accept. Now, okay. Now, what were we doing in the previous algorithm? We were flipping. If it accepts, we reject. If it rejects, we accept. If it rejects, we accept.
Hmm.
We reject, and so on. Oh, sorry. Before I come
Hmm.
to that, so M says accept, and therefore, what does it mean? Since there is at least one accept, it means that particular X belongs to my language because M accepted.
X belongs to L. Okay.
Right. X belongs to the language, whatever M is deciding, M is computing. Right. Now, what am I doing? I'm trying to come up with an algorithm for the complement of that language, L bar. And how did I do it? By flipping. If it was accept,
Hmm.
I did reject. If it
That
was
step
rejected,
will change into reject step.
exactly. So now my claim is that this particular new machine is enough. Right. That is what my previous claim was to decide L bar.
Hmm.
Right. To decide L bar. Now
Hmm.
look at what this new machine M prime, which flips the output of M, does. It has at least one accept, right? Because the previous machine had at least one reject. Because we flipped it, it has at least one accept.
Hmm.
So what does this new machine do? It has at least one path where it accepts. So what will this new
Hmm.
machine M prime do? At least one path has accept. By definition, M prime will accept
Hmm.
because there is at least one path which accepts. Right.
Okay.
Now, what does it mean if M prime accepts? X does not, sorry, X belongs to L bar because M prime is supposed to decide L bar.
Hmm.
Right. Now, what is L bar? L bar is the complement of L. All the strings that are not in L.
Okay.
So,
Hmm.
what does it mean? X does not belong to L. Right. X is in
X
L
does
bar.
not belong to L.
Right. So, how can.
Mm-hmm. Okay.
Right. So, how can it be that X belongs to L also, X does not belong to L also? It can only be if our algorithm was wrong. Right. Our algorithm of flipping does not work here, therefore, because it is not able to correctly decide. It is giving us wrong outputs.
And flipping is not working here, right?
Right. The technique is not working here. That is the key takeaway. Getting it?
Okay.
So algorithm is not working. Why? Because it is wrongly telling us that X does not belong to L, whereas X was belonging to L in the beginning. So obviously it does not decide L bar. So this algorithm, the previous algorithm of flipping, yes to no, no to yes, does not work in the non-deterministic context. Okay. This is all I was trying to say. Okay. That time. Now is it clear?
Yes.
Okay, it seems like it seems like a yes. That does not sound very convinced.
Yeah, actually, I'm not very convinced. Like, I got it, but I didn't get it.
Yeah. No, it's okay. Uh, but see, once look through it, try to work it out yourself also once. Okay, check it out in the video.
Okay.
I mean the video recording. It will be
Actually,
uploaded to
I'm
YouTube.
very familiar to TOC. Okay.
Yeah,
I'm very familiar to TOC.
right. You're
So,
familiar with TOC,
I actually have Michael Sipser's book
right?
for
Michael Simpson's book,
TOC.
right. And
Okay. So,
but this is mentioned in Sipser's book also in the NFA for non-deterministic finite automata. Same problem occurs. You can read that part in Sipser's book also, but you can
in
re
NFS section, actually, I have book right now. Okay,
yeah.
in NFS section.
Sure.
Okay.
The there is a section which talks about complement. Okay,
Compliment.
complement of for a non-deterministic finite automata. Okay, NFA complement, and read that section. Look at the YouTube recording and try to work it out. We'll meet again on Tuesday 6 p.m. Okay, and if you still have a doubt, we'll discuss it. Is that clear,
Okay.
sir?
Just one more question.
Right.
How many, like, are we going to discuss generic algorithms or fuzzy sets and on, or just computational things?
Fuzzy sets. No. That is outside the scope of this course.
Okay, and generic algo and or like decompositional, like I'm forgetting that algo names.
You mean like algorithm design techniques, like dynamic programming and sorts? They will algorithm
I'm not
design.
actually very familiar to that algo. Okay.
Right.
Okay, let me check that. I think I have.
No, the algorithm design
It's
techniques will not
like,
be will not this.
not designing techniques. It is actually to. mm, it is doing for to solve complex problems.
Right. Okay. But okay, I'm not sure. But you can check the course offering once, okay, and check the list of items that will be looked at in this particular course. But it is purely from a complexity theoretic point of view. It is not a direct algorithm design course as such, okay. And algorithms we'll be using as a tool here, okay. Not we are not studying
Okay.
algorithms itself, okay.
Okay.
Okay then, Seth.
Okay. Thanks.
Okay, thank you, Seth. Okay, look into this
Bye.
content. We'll meet again on Tuesday 6 p.m. Okay.
Okay. Bye.
Okay, great. Okay, bye.